Before getting to the experimentation and math portions of the assignment, we'll start with the explaining of what the actual device was built for. The device is essentially a slingshot. The wood is built in a way so that it can support the amount of kinetic tension that is going to be caused by pulling in on the elastic bands. The bands are wrapped tightly so that when they're being pulled on, they have more potential energy, which is critical since potential turns into kinetic energy needed to get the golf ball to the 10 to 20 meter mark. The red tape in the middle functions as the pouch part of the slingshot where the ball is held until release. The two planks in the center normally work to keep the two sides of the slingshot connected, but also are a foothold or somewhere to put a weight so that the device doesn't move when pulled on and affect its angle. For measuring angles, we have the wood planks going down to guide the 45-degree angle we need. To further be assured of the angle, a protractor is used to measure the angle on release.
We have our launcher, and it's going to be launching for the first one, which is 10 to 20 meters away. This right here is 10 meters. This final point right here is 20 meters. So he needs to hit it in between these two. So then that was right here. And we'll take that measurement afterwards. The next one he's doing has to be 5 meters away, which is around 16 feet or 15 feet, which means he has to hit a target that's right here, which instead of that, we are going to use a backpack. So in order to hit 5 meters, he has to hit this backpack. Try. Okay. I tried it. Take it. This works. Wait, I can take it to the back. Get it. Close. I got that. I'm just going to she said that.
So that hit.
So I had this tape measure also where we want it to hit. So this entire area was where we wanted it to. So it's right here, which is where we need it to be. So next we're gonna try and hit something that's in the air. So I'm gonna pull back, and we got it. Not against that, but right here.
Right.
So,
How do I put the size of it right there?
it's on right there.
Yeah, why don't you go back? We're gonna try to hit that, guys.
Okay. So like over here, measure it.
Where's the chalk?
Like the height. So grab measure tape. Just let me see.
Okay. So according to what I saw, it hit right here on the S. So if I measure it right, so it hit right around the S. So then that would be an estimate of 1 foot to 20 inches.
Okay. So this is our estimate for that.
So it's on 1 foot? I got 1 foot. And 20 inches.
So for the next one, we have to find our max. So for that, kind of worrying. We said each of these is, okay, so what we found out earlier was that each of these boxes is 80 inches. So we're gonna put this back and see how many boxes it gets to as our max. Can you hear this? Let's go all the way. So basically what we're doing is we're gonna measure the amount of boxes it goes. So you're gonna, as hard as you can, pull on it.
Alright.
We're just gonna start at this one so it's away from a window. So this marks 0. Like this is exactly at 0. And then each of these is 80, so we're gonna mark down where it hits and count how many boxes away it is to figure out our furthest distance. Okay, so then I'm gonna go down and mark where that hit, and that's our maximum.
Math involved in the first scenario, which is hitting an object from 10 to 20 meters away, or what we used was feet, so 39 feet 9 inches to 65 feet 7 inches. Here we have the table so that we can find out what our initial x velocity and y velocity was. And so the only thing that changes regarding anything because of the slingshot is we use the same angle for each one because we release at the same point, but it's the amount of pressure we are using to pull on the actual slingshot, which means the only thing that's really changing is the feet per second once released, which is what we're looking here for. And we also need to find the v of x of o, v of y of o. So first we fill in our chart. We knew that we start 1 foot off the ground for the y because the slingshot does not reach all the way to the floor. And then 0 for x, and then we end up at 51 feet. That's where we went because that's in between where we need to be. And our y ends up 0 because it hits the ground. We're looking for these two variables, and we know that it happened in 1.5 seconds. And then our here is negative 9.8, which will stay the same. So what we did to find it is we just insert our values into the equation. And so we were able to do that in order to get 34 as our x here. So we got that, and then using the same equation that we did for that one, we plugged in all our y values. And here's the math we did for that, which is just filling in and then subtracting from both sides, adding on both sides, and then subtracting here, and then that's how we did it. We did our final division, which got us this number, which just using Pythagoras theorem, we were able to get what our feet per second, so the amount of the feet per second on release. So that's what we used to be able to do that. The math remains pretty much the same for all scenarios because we are just looking for the singular change that happens in each of them, because all that is changing is how much we are pulling on the slingshot. So this one we went 5 meters, and so we were able to get all of our information here and here. We just need to look for this and this in order to get measurement right here. So for this one, we put in all of our information and we got 18.75 for here and then 5.17 for here. And then that's how we got this number right here. So it was released at 19.449 feet per second. There's a slight change in this equation because we do actually have a different final y because we are counting where it hit on the target that was in the air. So our final y is in the air and then it was at this point here. So all we did is just insert this for our y, which is typically 0. And so doing the math here, we get down to 5.733, which was our value for right here. And then we just cut down on the equation. It's short to this because it cancels out. Since this is 0, it's going to cancel out what we did for right here. And then this is 0, so it just cuts to right here. And so using theorem, we were able to get this is our feet per second on once we released, which is how it went that far. The way we found our maximum is by pulling it as hard as we could to see how far it would go before our band started breaking. And so by doing that, this was the absolute maximum we could get it to go forward without any ripping, which would mess with our calculations. So it ended up going 120 feet in 3 seconds. And so we just put in the math that we did for everything else. We were finding these two, which we got here, which was this number right here, and then this number right here, which makes sense because this is the fastest feet per second we got in the entire project, proving that that is stronger than the other ones. So that is our max.